Now, let us understand the escape speed. As the name suggests, it is the minimum speed required to throw any object out of the given gravitational field. This is called the escape speed of any object. Let us find the escape speed for Earth. We are throwing an object from height h from the surface of Earth of mass m. Now, to throw the object out of the gravitational field, we have to provide the kinetic energy that is equal to the total energy of this object at this place. This object is at rest at this place, so it is just having a potential energy. So we have to provide same amount of kinetic energy in order to escape it from the gravitational field. So the kinetic energy required will be equal to the magnitude of potential energy. Let's say we are throwing it with the speed of v. So kinetic energy given will be half mv square plus initially it was having some potential energy, that is minus gm em upon re. Now we are using the conservation of energy. This is the initial energy. Now when it reaches the point where it is out of the gravitational field, its potential energy will be 0 because it is out of the gravitational field of Earth, and it will come to rest because it is the minimum speed. So after reaching to that point, the object will come to rest. So its final kinetic energy will also be 0. From this, we can write half mv square is equals to gmem upon re. This m will get cancelled out as we are throwing from point that is above surface of Earth at height h. This will be re plus h. So v square will be equal to 2 gme upon re plus h. So v will be equal to under root 2 gme upon re plus h. This is the minimum speed required to throw the object out of the Earth's gravitational field. So this is called v escape. So escape velocity will be under root 2 gme upon re plus h. This is the case when we have thrown the object from height h above the surface. If an object is thrown from the surface of Earth, then h will be equal to 0. So v escape will be equal to under root 2 gme upon re. If we divide and multiply this equation with re, then v escape can be written as under root 2 gme re upon re square. But gme upon re square is gravitational acceleration on the surface of Earth. So we can write v escape is equals to under root 2 g re. Put the values of 2, g and re. G is 9.8 meter per second square, re is 6400 kilometer. We will get the value of v escape is equals to 11.2 kilometer per second approximately. Here, note that V escape is independent of mass of the object. That means the speed required to escape the ball out of the gravitational field of Earth is same as the throwing satellite out of the Earth's gravitational field. Let us see one example based on that. The ratio of masses and radii of the two planets is 2:3 and 4:9 respectively. What is the ratio of the escape speed of their surfaces? As the objects are thrown from the surface, we can write V escape is equals to under root 2 gm upon r. 2 and g are constant, so V is directly proportional to under root m by r. So V1 by V2 is equals to under root m1 by m2 into r2 by r1. So V1 by V2 will be equal to, the ratio of masses is given 2:3 and the ratio of radii is given 4:9. So R2 by R1 will be 9 by 4. So V1 by V2 will be equal to under root 3 by 2. So this will be our final answer. In this question, for Earth to become black hole, what should be its radius, keeping the mass constant? Here, black hole is an celestial element from which even light cannot escape. So, for any object to be black hole, the escape velocity from it should be minimum equal to the speed of light, that is equal to 3 into 10 power 8 meter per second. V escape is given by under root 2 g r. Now, V escape is equals to under root 2 gm upon r. It is given that we have to keep the mass constant, so we can write V is inversely proportional to root r. So V dash by V will be equal to under root r upon r dash. Here V is the actual speed of escape from the earth and V dash is speed of light. So 3 into 10 power 8 meter per second divided by 11.2 into 10 power 3 meter per second is equals to under root 6400 into 10 power 3 divided by r dash. Solving this, we will get r dash is equals to 8.92 into 10 power minus 3 meter that is approximately equal to 9 millimeter. So the Earth's radius should be equal to approximately 9 millimeter in order to behave it as a black hole. Now let us see some important points regarding to the escape speed. The formula of escape speed, that is under root 2 gm upon r, can be applied to any astronomical body provided we substitute the value of mass and radius of that body. For example, for moon, mass of the moon is 7.36 into 10 power 22 kg and its radius is 1.74 into 10 power 5 meter. So if we substitute the values in the formula of escape speed, that is under root 2 gm upon r, we will get the value of escape speed as 2.38 km per second for moon. The escape speed from a point on the surface of the earth may depend on its location on the earth, because we know that the escape speed from the earth's surface is under root 2 GRE. As the value of G is different at different points and radius of earth is also different at different points. Taking an example of equator and pole, the radius at equator is more than radius at pole and G at equator is less than G at pole. So at the different location, as the value of G and R are different, we will have different escape speed. The escape speed is more on poles and less on equator. The average value of escape speed is 11.2 km per second, but it may vary from location to location. The escape speed does not depend on the direction in which the projectile is fired. That means if you throw the projectile in any direction from Earth, as long as you are throwing it with minimum speed 11.2 km per second, it will be out of the Earth's gravitational field. However, attaining that speed is easier if the projectile is fired in the direction the launch site having as the Earth rotates about its axis. That means if the rotation of the axis and the launching of projectile, if both are in same direction, then we can easily achieve this high speed 11.2 km per second. Next, the value of escape speed does not depend on the mass of the projectile, because there is no term for mass of object in the formula of escape speed. It depends on mass and radius of the planet only. The escape speed is under root 2 gm upon r. If we want to write it in the form of density, then mass can be replaced by density into volume. Here rho is the density and volume will be 4 by 3 pi r cube. So in solving this, we will get 8 pi rho g divided by 3 into r square. Taking it out of the square root, we will get into r. So we can also write escape velocity in form of density and radius. The minimum kinetic energy for escape speed is equals to half mv square. That will be equal to the potential energy of the object on the surface, but its positive value, and that can be written as mgr. Because if we multiply this with r and divide with r, gm upon r square can be written as gravitational acceleration. The next point, if a body falls freely from infinite height, then it will reach the surface of Earth with a speed approximately equal to the average escape speed. This can be proved by using conservation of energy. If we throw an object with speed of escape speed, then finally it will reach up to infinite height and its speed will be 0. So if object is thrown from infinite height or it falls from infinite height, it will hit the Earth's surface with speed that is equals to approximately Earth's escape velocity. In calculating the escape speed, the air resistance and the gravitational effect due to other celestial bodies are neglected. We have not considered the air resistance, that's why only we can apply the conservation of energy, and we have not calculated or concerned the other forces applied by other celestial bodies. Now, if a body is projected with speed Vi is equals to kVe, where k is greater than 1, that means we are throwing a body with a speed more than that of the escape velocity, then the final interstellar speed will be under root k square minus 1 into Ve. If it is thrown with a speed is equals to kVe, where k is less than 1, that means we are throwing the object with a speed which is less than the escape speed, directly vertically upward. Then the maximum height from the center of the Earth attained by the body is r is equals to capital R upon 1 minus k square, where capital R is the radius of Earth and small r is the distance from the center. So its maximum height from the surface will be, subtract the radius of Earth from this equation, we will get r upon 1 minus k square minus r, that is equal to r k square upon 1 minus k square. These are the values for k is equals to 1. Now just the example that we have seen. For Earth to become black hole, the escape speed must become equal to or more than the speed of light. That is, under root 2 gm upon r should be greater than or equal to c, where c is the speed of light, that is equal to 3 into 10 power 8 meter per second. In that case, radius of Earth will become so that of size of a grape. The atmosphere on a planet is possible only if Vrms is less than V escape. If the atmosphere's gas molecules have RMS speed that is less than V escape, then only they will be surrounded around the planet due to its gravitational force. If Vrms is more than the escape speed, then the gas molecules will escape from the gravitational field of the planet and there will not be any atmosphere. So if Vrms is greater than V escape, then there will be no atmosphere. Now, let us see the shapes of trajectories corresponding to different velocities. Now, let us solve an example. What will be the escape speed from a planet having mass 8 times that of Earth and diameter 4 times that of Earth? The escape velocity is given by under root 2 gm upon r. So we can write V is directly proportional to under root m by r. So V dash upon Ve will be equal to under root m dash upon mass of earth into radius of earth divided by r dash. So v dash divided by ve can be written as under root mass is 8 times that mass of earth, so me divided by me into radius of earth is 4 times that of re. This r will get cancelled out, mass will get cancelled out, so v dash upon ve is equals to root 2. So v dash will be equal to root 2 times ve. So v dash will be equal to root 2 11.2 kilometer per second. In this question, we want to find what will be the ratio of escape velocities from surface of two planets having ratio of density as 4:9 and the ratio of radius as 5:3. The escape velocity from surface of any planet is given by under root 2 gm upon r. If we write this mass as density into volume, so V will be equal to under root g rho 4 by 3 pi r cube divided by r. That will be equal to under root 4 by 3 rho g pi. This will be r square. So out of the square root r. From this we can write that V is directly proportional to root rho into r. So V1 by V2 will be equal to under root rho 1 by rho 2 into r1 by r2. Given the ratio rho 1 by rho 2 is 4:9 into r1 by r2 is 5:3. So V1 by V2 is equals to under root 4 by 9 will be 2 by 3 into 5 by 3. So the ratio of velocities will be 10 by 9.